the distinct, got it. Okay, today I have the distinct honor to introduce Dr. Devon Crawford, who is the Program Director of the Office of Research Quality at the National Institute of Neurological Disorders and Stroke. The Office of Research Quality at NINDS focuses on changing scientific culture to more explicitly value experimental and analytical rigor, measures to reduce bias and transparency of reporting. Dr. Crawford received her Ph.D. in neuroscience from Washington University School of Medicine in St. Louis and completed a postdoctoral fellowship at the University of Texas Southwestern Medical Center. As part of an effort to promote Rigor champions, she contributed to a seminal publication on scientific rigor entitled Framework for Advancing Rigorous Research, published in 2020. She is presenting today on rigor, transparency, and NIH grants. So please join me in welcoming Dr. Crawford.
All right, thank you. Let me share the screen. All right, do you see that?
Yep.
Everything looks good, great. Okay, so let me adjust so I can see. Yeah, so first of all, I want to thank you all for actually having me here today to talk about what I think is a really important topic, which is scientific rigor and transparency. And today I'll be discussing it in the context of NIH grants. But I do want to say that my scientific background is more in the area of preclinical animal research, which I understand might be a little bit different than most of the audience today, but I do plan to discuss sort of the general concepts around rigorous science, as well as why it's important to NIH-funded research, and then also how it's integrated into guidelines. But I do need to begin by first saying that any opinions I express are my own, and I don't speak on behalf of the government today. Now, as Kathy mentioned, I am in the Office of Research Quality at the National Institute of Neurological Disorders and Stroke, which I'll just say NINDS from now on. And in this office, we live and breathe rigor and transparency efforts. You know, our general mission is to make sure that we are funding, quality research projects and not just the flashiest science. And in order to do that, we work both internally at NIH on policies related to rigor and transparency, as well as externally on things like initiatives and education and giving talks like this in order to improve research quality. And NINDS at NIH has actually been at the forefront of trying to improve rigor and transparency. And I'm going to be getting into that a little bit more in the talk itself. But first, I want to start with this, which is that many people often discuss this topic in terms of the need for reproducibility, but I'm going to argue that that isn't necessarily the primary goal. But before we get into that, I need to make sure everybody's on the same page. So these are just some quick definitions. And according to the 2019 National Academies report, reproducibility is obtaining consistent results using the same input data, computational steps, methods in code, and conditions of analysis. And so this definition is synonymous with computational reproducibility, whereas replicability is obtaining consistent results across studies aimed at answering the same scientific question, each of which has obtained its own data. So under these definitions, reproducibility is more about internal consistency within a computational workflow, whereas replicability is more about consistency across different experiments. Although some fields, some people disagree with these definitions, they're not always consistent, but we'll go with these for today. But the point I wanted to make is that just because something might be both reproducible and replicable doesn't necessarily mean that it can't be systematically biased, because the experiment might be designed improperly or not in the best manner possible. And just because something might be replicable doesn't necessarily, or not replicable, does not necessarily mean that that entire experiment is completely invalid, because it might be that the context matters for the experiment itself. And so because of this, we at NINDS tend to stick to promoting scientific rigor and transparency, hence the title of the talk. And according to the NIH definition, scientific rigor is the strict application of the scientific method to ensure unbiased and well-controlled experimental design, methodology, analysis, interpretation, and reporting of results. Whereas transparency for today, we will say it's reporting of all relevant details about how an experiment was planned, executed, analyzed, and interpreted. So this includes unexpected and inconvenient outcomes. And so we see these as necessary first steps to make sure that an experiment is valid before we can even start to think about its replicability, if that makes sense. Now, why are rigor and transparency so important? Well, everyone has unconscious biases that affect how we interpret the world. And Francis Bacon even said in 1620 that the human understanding, when it has once adopted an opinion, draws all things else to support and agree with it. And though there be a greater number and weight of instances to be found on the other side, yet it either neglects and despises, or else by some distinction sets aside and rejects, in order that by this great and pernicious predetermination, the authority of its former conclusions may remain inviolate. So, in other words, we tend to confirm what we already believe to be true. But how does this manifest in our research? Well, unconscious bias can often lead to experimental bias that skews results. David Ransohoff wrote in 2005 that bias is unintentional and unconscious. And so we are not talking today about intentional bias or misconduct. He says it's defined broadly as the systematic erroneous association of some characteristic with a group in a way that distorts a comparison with another group. But he went on to say that the potential for bias to affect results and interpretation can't be addressed by just a simple process. You need to make sure that everything is equal during the design, conduct, and interpretation of a study, and report those steps in an explicit and transparent way. And the first part of that phrasing probably seems pretty self-evident, but as for the second part, real-life experiments will always contain both known and unknown confounding factors. So reporting all of those details, i.e. transparency, is especially key, because after all, if you can't identify what actually happened in an experiment, there's no way you're going to know whether or not it's performed rigorously or, without bias. And this is one reason that a lot of guidelines have popped up to help researchers with design and reporting of studies. And here I just have the example of the consort statement, which is the consolidated standards of reporting trials. And this has been updated multiple times since the 1990s. But what it is just a checklist of 25 items that should always be reported for all randomized controlled trials. And they actually say in these guidelines that randomized trials can yield biased results if they lack methodological rigor. And to assess a trial accurately, readers of a published report need complete, clear, and transparent information on its methodology and findings. Now, as an example of how unconscious bias can creep in, this is a meta-analysis from a systematic review of human studies where they compared the effect size of the particular outcome measure between blinded and unblinded assessors in the same study. And this graph shows the standardized mean differences between the blinded and unblinded assessors, which is like a normalized effect size. And overall, the researchers saw this increased effect size in the unblinded outcome, which you can see in the blue diamond at the bottom. And what they said is that in 63% of their trials, the effect size point estimate was more optimistic, i.e. there was a larger difference seen as determined by the non-blinded assessor. So the standardized mean differences were actually exaggerated by a pooled standard deviation of 0.23. So this shows that when measures are not taken to try to reduce these unconscious biases through things like blinding, and it also happens with randomization, then the people doing the experiment may be more likely to find what they were hoping to see in the data, which, to emphasize my point earlier, creates a fairly replicable but biased result, right? And this is another example of experimental bias, but this time it's due to sample size. So, as many of you know, a typical study usually aims to have about 80% power to detect the difference between groups, but often the actual power is much lower. And so this figure shows data from 660 meta-analyses from 3 different disease areas, where the authors used the effect size that was found in each meta-analysis to estimate the power of each of the original studies that contributed to the meta-analysis. And as you can see from this histogram, about half of the original studies had less than 20% power to detect a real difference between groups. But, what is the consequence of having low power? Well, on the right, you can see a graph of the effect size versus the sample size in these studies. And you can see that the effect size negatively correlates with the sample size, meaning that studies that had a low sample size actually had inflated effect sizes, just like the studies we discussed earlier that weren't blinded. And so being underpowered can also lead to bias in the results. And this is probably exacerbated by the fact that studies that have a low sample size but happen to have a low effect size are probably never even published, which itself is known as a phenomenon called publication bias. This is where only the most interesting results tend to get published. Let's say you want to answer a research question. So you put all this work into experiments, and great, you have a statistically significant and super interesting, exciting result. You want to tell the world about it. You're much more likely to work to get it published. But let's say that it's less exciting, or there's no statistically significant difference in the data. It's much more likely to get filed away. And there are a couple of reasons this might happen. It can happen because scientists choose not to publish because they see papers like this to be less valuable to their careers, but also because journals tend to require exciting, novel results in order to get published. However, selectively publishing only statistically significant results can be considered a form of p-hacking, which is one does whatever they can to make sure that the results that they share are statistically significant. And you can actually see evidence of p-hacking when you look at the published literature. This is a paper that used a blind rater to compile over 700 p-values from published papers in the psychology journal. And you'll notice that frequency of p-values jumps right below p equals 0.05, suggesting that there are many more barely significant results than one would expect. Now, although some attribute this anomaly in the distribution to fudging of non-significant analyses in order to appear significant, just so that way they can get published, it also suggests to me that non-significant studies are not being published at their expected rate, because it is very unlikely that most experiments people perform are producing these significant results. Now, with publication bias, because we are missing many of these non-significant studies, we're likely only seeing a skewed version of the story whenever we're looking at the published literature as a whole. And this becomes especially important when we're trying to synthesize all of the studies on a given topic. For example, when we are performing a systematic review. In these cases, you really want the underlying literature to be both comprehensive and trustworthy. And as we just discussed, we know that it's not comprehensive, which can be a problem. But can we even tell if what is published is actually trustworthy? Well, one way to do this, for example, Cochrane reviews do this, is you can perform a risk of bias assessment to determine whether or not the underlying studies are transparent and have a low risk of bias. But unfortunately, a lot of times papers don't actually report or perform these important experimental design elements, and that leads to an unclear or high risk of bias, which you can see here in this example. There were 17 studies from 13 trials included in this systematic review, and you can see a lot of yellow and red for unclear or high risk of bias, which makes it pretty hard to interpret the cumulative evidence in this research area. And the authors even said that we detected a significant risk of bias across all included studies. And so this is largely due to a lack of blinding, as well as unclear methodological reporting. So a major question in my mind when I'm looking at something like this is, how much waste is this causing? If we can't even interpret the results of the studies we publish, and then we don't even publish all the studies that we're performing, right? But I want to make it clear that I'm not laying the blame for lack of rigor and transparency squarely at the feet of scientists, because they are not performing their work in a vacuum, right? They are under various pressures. There are things like professional standards that expect high quality work and a certain level of productivity. There are journals that pit scientists against each other to tell the flashiest and most exciting story if you want to even get published in the first place. And then funders and the peer reviewers at funding agencies that take publication productivity into account, both whether or not those articles are published in high-profile journals whenever they're thinking about, the investigator's history. And then on top of it all, institutional promotion and tenure committees, they rely heavily on things like publication record and funding history whenever they're deciding on career advancement. And so careful scientists can actually be punished in an environment like this. So all of these stakeholders need to take responsibility for fostering a culture that incentivizes rigor and transparency. Now, as someone who works at a funding agency, I would be remiss if I didn't start by pointing the finger at funders to ask, what have they been or could they be doing? But it turns out that NIH and NINDS specifically have actually been pretty active in this space for a while, so I'm going to be taking some time to go through that. Now, to explain why and how NIH got involved, I want to begin first by telling you two quick stories from the perspective of NINDS specifically. And NINDS, for context, is just one of 27 institutes and centers at NIH. Its mission is to seek fundamental knowledge about the brain and nervous system and to use that knowledge to reduce the burden of neurological disease for all people. And to support this mission, we do things like supporting and performing basic translational and clinical research, as well as funding and conducting research training and career development programs, and then promoting the timely dissemination of scientific discoveries. And one area of interest for NINDS is, of course, developing treatments for spinal cord injury. As famously happened to the actor Christopher Reeve, an accident or a trauma can injure the spinal cord and leave people paralyzed for life. But by the early 2000s, NINDS had already invested for decades in preclinical animal and in vitro work to try to find possible treatments. But despite dozens of promising leads, none had actually successfully translated into clinical therapies to help people. And so in 2002, NINDS released what's called a request for proposal to hire laboratories to independently replicate preclinical spinal cord injury studies. The goal here was to find the most promising approaches before investing in clinical trials. And then NINDS renewed the request a few years later. But ultimately, NINDS contracted 3 laboratories to do the work. And a summary of the outcomes was published in 2012. And I don't expect you to read this table, but the chart on the right actually shows what they found, which was that less than 20% of the attempted experiments could actually be replicated, and a full half of the studies showed fundamentally different results from the original studies. And of course, this was really disappointing, but it actually turns out that it parallels the results of many replication projects that have actually happened since that time. I don't know if you've all seen recently the reproducibility project in cancer biology came out, but there have been many replication projects and they find very similar things. But one reason that replication was so difficult was that the original papers lacked enough experimental details for the replicators to follow, getting back to that issue of needing transparency before anything else. And in fact, many papers today don't even report important items like blinding, randomization, sample size estimation. And you can see that in the study. They use text mining algorithms and they measured reporting in over 1.5 million papers in PubMed. And despite some gains over the last 20 years, you can see that reporting is still pretty low. Randomization is about 30%, sample size estimation and blinding about 10%. And so this isn't just a problem of the past. We still have a long way to go to improve reporting of items like this. But now I want to quickly switch to the second NINDS story, which relates to ALS research. And for those of you who don't know, ALS is a degenerative motor neuron disease, and Lou Gehrig and Stephen Hawking were high-profile people who had ALS. But there is no cure, and people often die within a few years of diagnosis. So because of this, just like with spinal cord injury, NINDS is really motivated to find treatments for ALS. But around the same time as those spinal cord injury replication studies, which was in the early 2000s, the antibiotic minocycline showed promises of potential ALS treatment. It improved both survival and motor symptoms in a mouse model of ALS, the SOD1 transgenic mouse model. And you can see an example of that here, where minocycline improved survival by this rightward shift in the survival curve. And this result is seen again and again and again, which is pretty replicable, right? So due to these exciting and seemingly replicable results, NINDS actually funded a clinical trial of minocycline in human ALS patients. So this was multi-center placebo-controlled trial, over 400 patients, 9 months, but the patients didn't actually improve on a functional rating scale, nor did they improve in terms of what's called freedom from failure, which is shown here. It's like a survival curve, but failure is defined as death, tracheostomy, or near total dependence on a ventilator. And this was, once again, very disappointing. And it raised questions about why the animal studies didn't predict how minocycline would respond in humans. You know, is it just that mice are not a good model for humans? Turns out in 2009, the ALS Therapy Development Institute published a study where they looked at factors that can affect SOD1 mice, which is the mouse model that we just discussed. And what they did is they took survival data from over 2,000 untreated mice from their own past studies, and then they ran simulations putting the mice into 2 groups. And then they measured what they called an apparent effect, so more than 5% difference in survival between the groups, which, you know, as you can tell, would be a false positive since these animals were all from a control group that didn't receive any sort of treatment. Now, when they didn't control for any sort of factors, and they had 4 mice per group, they saw apparent differences between the mice more than 50% of the time. You can see that here, more than half the time. But they were able to decrease this sort of false positive rate when they removed mice that had a low copy number of the transgenes, because these mice just tend not to be as sick. They removed mice that died of study unrelated causes like infection, and they implemented sex and litter matching. Now, if they increase the sample size, of course, they could decrease this rate even further. But had they never actually implemented any ways to reduce bias from these confounds, you can see that they never actually would have reached the 5% false positive rate that people often think of as an acceptable rate. So all of these things need to be considered in the experimental design, and controlling quality through reducing of these confounding factors can actually be really important for keeping the false positive rate reasonable, in addition to things like sample size that we discussed earlier. But anyway, the ALS Therapy Development Institute actually went back and performed brand new quote unquote optimized studies on drugs that actually failed in human ALS clinical trials, and minocycline is included here, and they did it in the same SOD1 mouse model. But these new optimized studies had things like a sufficient sample size. They had at least 24 per group. They controlled for the confounding factors that we discussed on the last slide. They blinded investigators, they randomized, etc. And what they found is summarized in this table, or this sort of horizontal bar graph. And the light blue bars are the prior studies, so you can see the increased survival in those prior studies. The dark bars are the results from the new optimized studies. And in every single case, you can see that the new optimized studies showed a small and sometimes negative effect of each drug on survival. And I will highlight minocycline here. You can see that huge difference. So imagine how much time, money, and patient risk could have been avoided if the original animal studies had just been performed more rigorously. So because of these experiences with spinal cord injury and ALS research, NINDS actually began leading the charge at NIH in order to change research culture to try to increase attention to rigor and transparency. And as an aside, I want to say that many of these efforts were led by Shai Silverberg, who's now director of our office. And as a start, NINDS released a notice in 2011 to the community about its expectations for rigor and transparency, saying that the design, execution, and interpretation of the proposed studies and the supporting data should be adequately described. And then afterwards, NINDS actually changed its clinical trial grant reviews to be 2-stage discussions. So the first thing they discussed is first the preclinical work that led to the clinical trial. How rigorous was it? Is the trial even justified, before ever discussing the design of the trial itself? And these reviews were held in-house at NINDS, they still are today, and not at the Center for Scientific Review at NIH, which is one reason we have so much control over it. But we didn't stop there. In 2012, NINDS hosted a workshop to discuss improving preclinical research, And the focus here is on transparency in preclinical animal research because, as you see, this particular scientific area seems to have the most deficiencies in reporting, I'll say. And this workshop brought together, researchers, peer reviewers, journal editors, funders, all to discuss, which experimental practices are important for controlling bias and therefore are most important to report in studies. Because as we discussed earlier, we can't exactly improve practice until we know what was actually done in the first place. And the workshop participants published a paper where they outlined a core set of items that should be considered when designing studies. And they should always be reported afterwards, regardless of whether or not it was actually performed. If you didn't perform blinding, for example, you need to say that you did not perform blinding. And those particular 4 items, I will say, are things like blinding, randomization, sample size estimation, and data handling. But I want to note that data handling includes things like inclusion-exclusion criteria. It's not just data analysis. But as you can see, these items are important to report for any kind of research. So the recommendations are pretty useful beyond preclinical animal research. And they are often now referred to as the Landis 4, after the first author, Story Landis, who was an NINDS director at the time. And following these activities, Story Landis actually gave a presentation to the NIH Advisory Committee to the Director, or ACB, in 2013. And this is a committee that gives advice to NIH leadership about NIH activities. And overall, the ACD agreed that we shouldn't be wasting time on experiments that are poorly designed, obviously, but that we should be bold in facing these issues. And then NIH leadership actually took this ACD response to heart after this meeting, and the NIH director, Francis Collins, and his deputy, Larry Kibbeck, who is now acting NIH director, by the way, published this comment in 2014, making a public NIH commitment to rigor and transparency. And in it, they described 4 major things that they wanted NIH to do. First, provide better training in rigorous experimental design. 2, increase attention to rigor in grant applications. 3, increase publication of raw data sets. And then 4, to partner with other stakeholders to change these incentives because they can't do it alone. And to kick off these changes, NIH actually released a notice to the community in order to let them know that grant application instructions would be changing, saying that they wanted to clarify longstanding expectations to ensure that NIH is funding the best and most rigorous science. They want to highlight the need for applicants to describe details that may have been previously overlooked, as well as highlight the need for reviewers to consider such details in their reviews. And then they also released an open mic blog post, which are blog posts by Mike Lauer, the director of the Office of Extramural Research at NIH. And this was in order to remind the community about the importance of rigor, as well as, warning them that the new application instructions would be emphasizing this. But around the same time, they also changed the NIH BioSketch to include major contributions to science instead of having you just list your papers. And these new instructions were actually implemented for most NIH applications submitted as of January 2016. And this notice here outlines the specific changes they made, which were first revisions to the application guide instructions for the research strategy, a new authentication of key biological and/or chemical resources attachment, as well as additional rigor and transparency questions for reviewers. And they said that these updates focus on 4 areas deemed important for enhancing rigor and transparency, and then they made a nice little graphic, and these are the 4 original items that they had. 1 is premise, the scientific premise forming the basis of the proposed research. 2 is design, so rigorous experimental design for robust and unbiased results. 3, variables, so consideration of relevant biological variables. And 4, authentication of key biological and/or chemical resources. And the first 3 are actually considered part of the scoreable criteria of the grant, but the last one is an unscored attachment to the application. And of course, these new areas of focus were meant to apply to the full spectrum of research, not, just basic. So it's basic all the way to clinical. But briefly, before I go into them, I want to talk a little bit more about this first criterion, scientific premise, which was defined as research that's used to form the basis for the proposed research question. In the notice, they say that NIH has always strived to fund projects that are based on a strong foundation. So moving forward, NIH expects applicants to describe the general strengths and weaknesses of the prior research being cited by the investigator as crucial to support the application. However, we at NINDS actually performed an analysis in 2017 asking whether or not applicants were following the new criteria. And we found overwhelmingly that many investigators and reviewers actually misunderstood scientific premise to mean the general rationale for a study. For example, applicants and reviewers might refer to the importance of asking a particular question, or saying that there are lots of studies that support asking a particular question. Instead, they should have been discussing the trustworthiness of those prior publications. And so we took this analysis to NIH leadership, and they actually worked fairly quickly to update the language, so that way they could clarify this. So what they did is they released a notice 2018 updating the instructions that for grants that are submitted after January 2019. And so, for example, they changed the language saying to describe the scientific premise, to describe the strengths and weaknesses of the rigor of the prior research. And so the term scientific premise has been completely removed. I still see grants to this day who refer to scientific premise as a criterion, but it is actually no longer in the instructions. Now, because of this update, they also had to change, this graphic with their 4 focus areas from what we discussed before to this, which is 1, rigor of the prior research, 2, rigor of the proposed research, and then biological variables and authentication didn't really change. And so this remains the current guidance today. And so now I'm going to quickly go through these 4 in just a little bit more detail, so that way everybody's clear on them. So the first focus area, as we said, is rigor of the prior research, not scientific premise. So this item asks applicants to describe the strengths and weaknesses in the rigor of the prior research, which is both your published cited studies as well as your unpublished preliminary data. That serves as the key support for the proposed project, as well as plans to address those weaknesses. Now, an important phrase here is key support for the proposed project. I want to emphasize that, this doesn't have to be done for all your cited studies and your preliminary data, just those that you're considering as key to justify your proposed experiment. And then NIH has also released more detailed guidance on their website saying that a careful assessment of the rigor of the prior research, it can help identify weaknesses or gaps in a line of research, and therefore NIH expects applicants to describe these general strengths and weaknesses in the rigor. But it's expected that this consideration includes attention to the rigor of the previous experimental design, as well as the incorporation of relevant biological variables and authentication of key resources. Now, it also goes on to say that applicants are expected to include plans to address any weaknesses or gaps identified. So, for example, if all the prior studies you identify are unblinded, not randomized, they have low sample size, then this will actually have to be addressed in the application of what you plan to do before you can claim that there's a strong foundation to build your next experiment upon. The second focus area is rigor of the proposed research, and these are the experiments you plan to perform. And as we discussed earlier, NIH defines scientific rigor as the strict application of the scientific method to ensure robust and unbiased experimental design, methodology, analysis, interpretation, and reporting of results. Now, this includes full transparency in reporting experimental details so that others may reproduce and extend the findings. And they also provide guidance saying that, what is meant by robust and unbiased? Well, robust results are obtained using methods designed to avoid bias and can be reproduced under well-controlled and reported experimental conditions. Applicants should consider methods to reduce bias, such as having multiple individuals recording assessments or defining terminology in advance, using independent blinded assessors, etc. But you may notice that NIH refers to reproducibility here when they might actually need replicability according to the definitions that we outlined earlier. So be aware about that difference in definition. The third item is biological variables such as age, sex, weight, and underlying health conditions, because they are often critical factors affecting health or disease. Does say that NIH expects that sex as a biological variable will be factored into research designs, analyses, and reporting in vertebrate, animal, and human studies. Now, although NIH emphasizes sex as a biological variable, as well as, it's always good to have both sexes as a way to improve generalizability of findings, remember that sex is not the only biological variable that can confound studies, as we learned earlier. So I suggest that applicants don't forget about these other variables when designing experiments. I do see that a lot. The focus on sex as a biological variable, but then forgetting about all the other biological variables that can affect your experiment. And NIH includes additional guidance saying, which relevant biological variables should you consider? Well, those that are relevant to the particular experimental design of the study you're performing. And the choice of animal model or human population, may vary with the scientific topic. That makes sense. So things like sex, age, weight, and underlying health conditions are just examples of biological variables that could affect health or disease. And the fourth item and last item, thankfully, is key biological and or chemical resources. So these include, but are not limited to, cell lines, specialty chemicals, antibodies, and other biologics. The quality of resources used to conduct research is critical to the ability to reproduce results. Again, they probably mean replicability here when they refer to reproducibility, so keep that in mind. But this is, as I said before, an attachment to the application, and it's not part of the scorable criteria, unlike the first three items. But in this attachment, you must briefly describe methods to ensure the identity and validity of key biological and or chemical resources. However, standard laboratory reagents that you don't expect to vary a lot don't actually need to be included here. But whatever you do, do not put experimental methods or preliminary data in this section. Focus on the authentication and validation of those key resources. And because these four items have been added to the instructions, reviewers are now additionally asked 4 questions that they weren't asked before when they're reviewing the application. For example, related to that first criterion, rigor the prior research, they will be asked, is the prior research that serves as a key support for the proposed project rigorous? They will also be asked, have the investigators included plans to address weaknesses in the rigor of the prior research? And for the next criterion, they're asked, have the investigators presented strategies to ensure a robust and unbiased approach? And then the third criterion, have the investigators presented adequate plans to address relevant biological variables? But they will also be asked to comment on the attachment for authentication of key resources, but they will just judge that as acceptable or unacceptable. Now that we've gone through all of that, I want to remind you that those are just the general NIH guidelines. You should always read every part of the funding opportunity announcement or FOA for which you're applying. Each one can have its own specific language for what's required, and that can include specific rigor and transparency guidance. So, for example, this is a T32 training program that puts a heavy emphasis on training in rigor and transparency, where the training program plan must address things like training in experimental design, statistical methodology, quantitative literacy, scientific rigor. And on the right is an example of a translational science program that also includes strong language saying that the research plan must address things like strength and quality of the data used to provide the basis for the chosen measures, feasibility, reliability, and comparability to practical clinical assessments, key metadata to enable reproducibility, as well as design and statistical approaches to establish reproducibility and test internal and external validity of outcome measures. Now, it's unclear whether reproducibility here means computational reproducibility or replicability or both. So once again, be aware of those differences in the definitions. But overall, a good piece of advice that I want you to take away is that you should always read the FOA. Always read the FOA. Now, NIH also has plenty of websites with general guidance that you might find helpful. On the left is just an example of a website that has what you should be reporting in publications. On the right is an example of resources for integrating rigor and transparency into your actual grant applications. So feel free to check those out if you haven't already. But switching gears, I want to talk more about where NIH is going in the future. So I wanted to let you know about other activities in this space. For example, in June 2021, which wasn't that long ago, the ACD Working Group on Enhancing Rigor, Transparency, and Translatability in Animal Research, so that's a mouthful, they presented a report to NIH leadership, and Shai Silverberg from our office was actually an NIH member of that working group. And this is a working group that was charged to identify gaps and opportunities to improve rigor and transparency, which they also acknowledge is not exactly a new goal at NIH, but they specifically focused on animal models in order to improve translatability, because as seems to keep coming up. It's a perennial problem of this issue of animal models translating into clinical trials. But the recommendations that they made are here. The first one is their primary recommendation of the 5, and it is to improve study design and analytic rigor. And under this, what they really wanted to emphasize was enhancing statistical training, statistical collaboration, as well as statistical review. But they also suggested that NIH dedicate an entire page of the application just to critical experimental design items. The second recommendation was to address bias, incomplete reporting, and questionable research practices. But this was mostly about promoting prospective study design, so that way you can prevent publication bias. Third is improve relevance and use of animal models. So this is just helping investigators match the animal model to the research question. 4 is improve methodologic and results reporting. So this isn't just adherence to reporting guidelines, but it's also tracking of animal care variables to reduce confounds, which we talked about before. And 5 was their cross-cutting theme. It's to measure and evaluate effectiveness and cost. So this is just assessing the success of these particular recommendations. But the point is that the ACD endorsed these recommendations. And so it's possible that there could be, policy or guidance changes coming out in this space in the future. So if that is relevant to you, keep an eye out there. But another change that we know is on the horizon relates to data sharing policies. So after years of public comment and vetting, there is a new requirement that will go into effect as of January 2023, and that is for data management and sharing plans. And they will be required for all applications, not just those above $500,000 or those with things like genomic data that were already required. They say in the policy that it establishes requirements for these plans. It also emphasizes the importance of good data management practices and establishes the expectation for maximizing the appropriate sharing of scientific data. And hopefully this will improve transparency of research. But there are a couple important things I want to note. And that's first that these plans will be part of the budget justification section of the application. Also, these plans must include consideration of accompanying metadata, not just the data themselves. And the data need to be shared by the time of publication. But if there is no publication, by the end of the award. And also, where possible, make use of established repositories. So gone are the days that investigators can just keep their data private, make it available upon request. But also, these plans will be deemed acceptable or unacceptable by program staff, not the reviewers. And so you should check out this notice for the full policy on that. But I have also provided a couple of websites if you'd like more data sharing resources. And on the left is the Office of Data Science Strategy. And on the right is a website that links to NIH-supported data repositories. So check those out. I know I have a lot of websites here, but I've been told that this will be recorded and posted to a website, so you can check them out after the talk. All right, so I've spent a lot of time so far discussing what NIH as a funder has been doing in this space to try to change culture. But with what little time I have left, I do want to mention just a couple examples of how these other stakeholders can also contribute to a better culture. For example, journals. They have a part to play, of course, in incentivizing researchers, not just to perform more rigorous research in the first place, but especially reporting that work more transparently. After all, I hope journals don't want to be known for publishing shoddy work, but they are the gatekeepers for scientists to show their productivity, right? But after NINDS held that 2012 workshop with publishers that led to the Land of 4, many actually came out with checklists with experimental design details that they required to be reported in their papers. And this is an example of Nature's checklist, which has, Land of 4 items like sample size, data exclusions, randomization, blinding. They also have replication and statistics. But as an aside, in order to ask how effective these checklists are, there was actually a study that looked at papers published before and after Nature Publishing Group came out with their checklist. And what they did is they gathered papers from Nature Publishing Group, which is on the right, as well as compared them to papers from non-Nature Publishing Group journals, and that's the control journals on the left. And they looked at papers a couple of years before and a couple of years after the checklists were introduced. And to orient you, in black are studies that reported that particular item in detail. Green are studies that gave the item a passing mention, and white are studies that didn't mention the item at all. And you can see 4, sample size calculation, randomization, blinding, and data exclusions. that there is a big jump in reporting after Nature Publishing Group came out with their checklist, especially in the NPG journal. However, only 16%, that is 16% of articles in the Nature Publishing Group journals actually reported all 4 items in a single paper, suggesting that the checklists help with reporting, but they're not exactly a panacea for promoting transparency. So journals, therefore, play an important role, but they do need better enforcement, and they clearly can't do it alone. But what about in the area of professional standards? Well, these standards include things like how researchers communicate their research to each other. Yet rarely do conference organizers actually explicitly ask for transparency in presentations. Like, think of your posters and your platform talks. Well, NINDS actually sat down with some conference organizers and published some tips in 2017 for how to make conferences and then data figures specifically a little bit more transparent. So we have an example here compared to your traditional bar graph here in the middle. You could instead, show all of your raw data points instead of just a summary. You can make sure to define your error bars as well as show the spread of the data, include sample size. And we also suggested at the bottom to include icons that indicate things like whether or not blinding and randomization were used, or whether or not it was a confirmatory or exploratory experiment. So this doesn't take up any more space, but it is much more transparent. And after this commentary, actually, FASA, which is the Federation of American Societies for Experimental Biology, they actually ran pilot studies at their smaller conferences where they tried to encourage adoption of these practices, which I think more conference organizers could try doing. And then let's look at institutions. How exactly can they change researcher behavior to incentivize good practice? Well, one way is to change how they assess researchers for hiring and promotion. And one movement in this area is DORA, which is the Declaration on Research Assessment. And this was developed in 2012 by stakeholders from various sectors. And what it is a statement on how scholarly research should be evaluated. And over 20,000 individuals and organizations have actually signed on to this at this point. And the recommendations they make are things like, not using journal impact factor is a surrogate measure of quality of the individual article. And then for institutions specifically, when they are considering hiring, tenure, and promotion, to look at the scientific content of the paper. Consider that as more important than publication metrics or what journal it's published in. And then also valuing other forms of research output that aren't just your traditional, scientific publication. And there have been similar efforts in the space, like the Leiden Manifesto or the Hong Kong Principles, if you've heard of those. But despite the fact that many institutions have signed on to DORA and these other particular efforts, many have yet to actually change their researcher evaluation criteria. So this is an ongoing process, just like everything else. And finally, we can't forget about the scientists themselves. So, we as scientists are incentivized to behave in ways that are inconsistent with best scientific practice because of these pressures, but we still have some agency, to change the culture around us. And so to help scientists find and support each other, we have actually proposed that they create communities of rigor champions. And NINDS held a workshop about this in 2018, and this table is from a commentary that the participants wrote, which might be too small for you to read in detail, which is fine, you can look up the paper. But it lists activities that different groups can undertake in order to support each other and change scientific culture. And as an example, individual researchers can do small things like just promoting rigorous practices among their colleagues and their trainees. But they can also work across institutions to share, say, effective training practices. And so I encourage anyone who's interested in improving rigor and transparency to try to get together with others and start your own communities. In this way, maybe we can start to address the less rigorous practices that can creep in at every stage of the research life cycle to create spurious results. We discussed today failure to control for bias, low statistical power, poor quality control, p-hacking, publication bias. As I said in the beginning, each of these things can occur without any sort of intentional fraud or misconduct, but they do work together to weaken the strength of scientific evidence in the literature. But this is my major takeaway that I want you to have from this talk. I believe that if we all do what we can to improve research quality just a little bit, then we can see a shift towards a better overall research enterprise. I'm saying that we don't each have to move mountains and create large change, but we can each take a little step here, a little step there towards a better future, and cumulatively, we will all be in a better place. If you take nothing else from this talk, I'd like you to take that we can all do a little bit. We can make one change in our next study, and then one change in the next study after that. And as a final note, I've included some additional resources here that might be of interest. We have our website for the office at NINDS. We have a Rigor Champions email address. We also have a Slack workspace for people who might be interested in being Rigor Champions. But there's also a webpage that we have of over 170 resources related to Rigor that you might find helpful. So, and if anything's missing from this list of resources, we are always trying to look for more and add them to this table so that way other people can find them. But with that, I want to thank you for your time. I'm happy to take questions. My contact information is here in case you'd like to follow up. But thank you.
Thank you. That was great, Dr. Crawford. Thank you so very much. We have about 6 minutes left for questions. So I wanted to see who might have a question for Dr. Crawford. It was a very thorough presentation. So anybody?
And I know it's a little dense, so feel free to watch the recording, get those resources.
Is there any chance we can get your slide set as well, because it might be easier just to copy from the slide rather than capture it from the video? You have to sort of type it all up. Is that possible?
Yeah.
Awesome.
Just email me and I can send you a copy of the slides.
I will do that. Thank you. And we can post both then. Awesome. Anybody else with questions? Everybody's
Someone
so
said I
quiet.
ran. So that's great.
Right? This is you're a crowd pleaser, I think. People are posting thank yous in the comments right now, and I want to thank you for an incredibly thorough presentation and taking time to spend with us today. It's really very kind of you to spend this hour with us. And we really appreciate your knowledge and your understanding of all of the resources that are available to us, and how we're going to have to sort of change our approach to some of our grant writing at this point, where things are changing in this direction. So thank you so very much. Anybody else want to say anything?
I had one question, because we have a lot of trainees on. This is Kate. Fabulous presentation. Thank you so much. I felt like it was a data download of all the information. It was wonderful. But I had a question, because we have a lot of trainees on the call, and I wondered about the power differential when they're in labs and so in our programs we have required rigor and reproducibility training, right? Like, and part of the seminar series that Kathy's put together and the curriculum that she and I had worked on, we're trying to integrate that across some of our training programs. But I recognize that because students and trainees, there's a power differential. I don't know if that's just one little piece of the puzzle to change the culture. And I keep thinking like, oh, we got to do more. How do we do more? So any advice to us as an institution?
Absolutely. We definitely recognize that. We actually notice that trainees are usually the most enthusiastic to implement these things, but they run into these barriers when they get to, their mentors who've been doing the same thing for 30 years and haven't been told that it's not okay. Right. And so they think, I've been doing it for 30 years. Why do I need to change? And then, of course, in order to work with that particular mentor, they have to do what the mentor wants. And we understand that that's happening, which is why, we suggest that trainees get together to support each other. For example, there's an international journal club called Reproducibility, with T is TEA because it was formed in the UK, and what they did is they got together and they had tea and they discussed rigor issues. And that's something that you can create a local chapter for, so the trainees can get together with each other, discuss these issues. But then you also need, administrators at universities. You need your deans, you need your department chairs. Everybody needs to be trying to change, being aware of these issues. We try to focus on education and awareness. And so if they're getting it from all sides, then they might think, okay, maybe I need to change. But we do recognize that that is really, really hard sometimes. So, try to find the support where you can, try to change the culture where you can, and hopefully overall it will, move forward.
We'll keep chipping away because, I'm
What you can do.
fascinated by, and I honestly, of all the NIH institutes, yours is at the forefront. I mean, in terms of materials and resources that we've tapped into. So thank you so much.
Absolutely.
Yeah, we try. We've really, this is something we've taken on and that we care a lot about, and we're okay being out there in the front trying to drag the rest of NIH along with us. So yeah, we're doing what we can.
Much appreciated.
Keep up the good fight.
Yeah, definitely. Thank you so much.
All right,
Yeah.
thank you. And thank you to everybody who attended. Really appreciate it. Thank you, Dr. Crawford. We'll have that video up in no time. Kelly's going to put it up and we'll have slides too. So lots and lots of resources for everybody. Thank you so very much and have a great day. I hope you don't get snow in DC.
Sunday.
Yeah, good luck.